Hello, this is Mr. Porter again, another installment in our Pascal's Triangle series. We're dealing with the same problem that we looked at in the past. If you flip a coin 5 times, what is the probability that you get exactly 2 heads? All right, so in the prior set of video, we looked at the tree diagram that represented this entire dynamic, and we identified that there were 10 options, 10 ways that we could get we could flip the coin 5 times, which would then result in 2 heads. Now, there are many other options than 10 to get more than 2 heads, or even less than, or even none. But if we wanted exactly 2 heads, there's only 10 options to achieve that. Now, what's the connection between this problem, this reality, and Pascal's triangle? Well, let's look at it. Again, Pascal's triangle begins with a 1 at the top row, 1 and 1 on the second row, and then we have 1, 2, 1, because 1 plus 1 is 2. Begins with 1, 1 plus 2 here is 3, 2 plus 1 here is 3, and then we have ending with a 1. Beginning the next row, which is a 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, ending with a 1. And then the next row begins with a 1, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is also 10, and then 4 plus 1 is 5, ending with a 1. Lastly, for this example, we'll go down to 6 rows. Begin with a 1, 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, 5 plus 1 is 6, and then ending with a 1. Now, I've only gone down 6 rows. I actually did not really need to go down 6 rows because we're dealing with a situation that looks like 5. Something happens here 5 times, which means I only really needed to go down to the 5th row. All right, so we're looking at some order, some arrangement that occurs 5 times, and I'm looking at specifically 2 events within those 5 arrangements. That definition is called a combination. A combination is an arrangement of entities or items in any order. The order is not important. And in this case, we're dealing with an arrangement of 5 events. In this case, the event is a flip. And we're looking at 2 specific scenarios or 2 specific elements, 2 cases within those 5. So this we read as 5C2. And there are various other ways of reading that, but I'll read it for today as 5C2, which is a combination where the arrangement or order does not matter, that we have 5 items in our sequence, and we're focusing on just 2 of them. This equals, based upon our findings from the actual tree diagram, 10. What is the relationship between this representation, 5C2, and 10 in Pascal's triangle? Well, if we connect that, if we look for a 10 in Pascal's triangle, we see a 10 is here, and there's another 10 here. That's specifically important. Now, what about the left side of this equal sign? How does this nomenclature of 5C2 relate to Pascal's triangle? Well, the first number, 5, which tells you how many items there are in the sequence altogether, is the row number. This is your row number. The number behind it, which specifies how many items you're specifically focusing on within the arrangement, is your position number. This is your position number. All right, so as we discussed in a prior video, in Pascal's triangle, we always start counting with 0. So this is row 0. Therefore, this would be row 1. And we specified in the prior video that the second number in the row, or in that particular row, tells you which row it is. So the second number in this row is a 1. That's why this is row 1. There is no second number in this row. That's why this is row 0. The second number in this row is 2. Therefore, this row is row 2. Second number here is 3, so this is row 3. this is row 4, and then this is row 5. Row number here, again, counting in Pascal's triangle, everything begins with a 0. So if I'm looking at a particular row and I want to get to a particular position inside the row, this is position 0. All things in Pascal's triangle start with 0 when counting. This is position 0. This is position 1. This is position 2. Let's go to row 3 and try to follow that same line of reason. This is position 0. This is position 1. This is position 2. This is position 3. In row 4, we have position 0, position 1, position 2, position 3, position 4. Now we're on row 5. Position 0, position 1, position 2. This 10 is in position 2 of row 5. So this writing format here is actually an address within Pascal's triangle. It tells you the row number and it tells you the position number. Row 5, position 2 will tell you how many options there are available if you had 5 items in your arrangement or in your sequence, in your chain, and you were only focusing on just 2 of them, like we're doing in this problem. We're flipping something 5 times. That tells us what our arrangement is, how many items there are in our arrangement, what our sequencing is. And then we're only looking at 2 of them. 2 of the identifiers within that arrangement. 5C2 means we can go to Pascal's triangle, go to row 5, go to position 2, and identify how many options there are. Don't forget, this also serves as a coefficient inside of a binomial expansion. So not only are these numbers coefficients for a binomial expansion, these numbers also represent the number of options there are if you were taking 5 items in a sequence and you were focusing on 2 of them at a time, or any number of objects. If I had 6 items in my sequence or my chain or my arrangement, and I was focusing on, I don't know, 3 of them, position 0, position 1, position 2, position 3. If I were focusing on 6 items in my chain or my arrangement, and I was looking, if I had 6 in my arrangement, and I was focusing on 3 of them, there would be 20 options that I would need to consider. So very shortly and quickly, this is the correlation. This is the connection between Pascal's triangle and arrangements in the tree diagram. Pascal's triangle is extremely powerful if you understand what the connections and the relationships are. Thank you for your time.